From 1992 until 2000, he worked at the National Institute of Standards and Technology in Boulder, Colorado. From 2000 until he joined the University of Maryland in 2007, Chris was a faculty member at the University of Michigan. In addition to being named a member of the National Academy of Sciences, Chris is also a fellow of the American Physical Society, the Institute of Physics, and the American Association for the Advancement of Science. Please join me in welcoming Dr. Chris Monroe to the stage.
All right. Thanks, Gene. Very helpful. All right, I got to turn this. Oh, it's on. Well, thank you, Gene, for the kind introduction and for you all being here. I don't often speak at a venue like this, but I'm glad that I'm looking at all those beer taps, and they've all had a few beers, because this is a subject that the more if you're not an undergraduate, the more beer you drink here, probably the better you will understand the subject. It takes a little bit of quantum physics takes a little bit of a leap of faith. But once you do that, you can become quite comfortable with it. And so my task here is to, I don't know, I'll figure it out as we go, but the most important thing is I want to convey to you that quantum physics is actually, it's not hard. It's very easy to understand the fundamental concepts behind it, and I'm going to tell you those. It won't take very long. The math can get complicated, but that doesn't add necessarily to any understanding. So that's the take-home message, that quantum it almost never appears in your daily life, so you don't really have to know it, but there is a set of technologies that is coming down the pike that involves things that are very strange, and I want to maybe give you just a little flavor of that stuff. So yeah, if you want to interrupt me at any time, just yell or raise your hand or something. Happy to step through. So I am a physicist by trade in the physics department here at Maryland. I run a pretty large research group, and we're actually by some arguments the biggest research group in a very particular area, and that is to control individual atoms one at a time. And it turns out this could be a new technology that could revolutionize computers, certain aspects of computers in the future. So I actually don't have that many slides. They're mostly pretty pictures, so they'll be easy to follow. This first picture here is it's a conglomeration of a few things, but you see those blue dots on the top there. Those are individual atoms. Each dot is a single atom. And it turns out these are, as you'll learn, as I tell you the laws of quantum physics, this system is the cleanest physical system with which to study quantum physics and actually to build a device that could be interesting. Each one of these atoms is a memory element in a so-called quantum computer. And what makes me nervous about this field is that we still don't know exactly what a quantum computer is useful for. I'm also a founder and a CEO of a startup company called IonQ. That's our logo right there, the Q there. And we're located right by the College Park Metro station in the old Trader building. And we're actually building prototype quantum computers. I'll talk very briefly about that. And the reason we have a company is that we're engineering this system so that it can be usable by others. And that's very difficult to do in a research setting. It's very expensive, and we need professional engineers and so forth. So I'll tell you a little bit about that story. So that's sort of the very long introduction. And yeah, there are a lot of ways to start out. But I think I will start out with this is a college of mathematics and computer science. So I will start out from a computer point of view, even though I'm not a computer scientist. This is probably the most complicated slide, and I'm sorry if you can't read anything, but you don't need to. I'll tell you what it is. this is a description of what's called Moore's Law. Now, Moore's Law describes the size of transistors over time. And so the horizontal axis is the year from 1950 or 1960 to the present. And the vertical axis is the number of transistors on processors. And this is an exponential, it's a log plot vertically. So this is exponential growth in the density of transistors. So now we're putting 10 billion transistors or so on chips. And the reason I put this up here is that Moore's Law cannot continue forever. Because if you keep going on this slope, eventually the transistors get so small that they're the size of individual atoms. And that's a problem because you can't, I don't think we want to split the atom inside of a processor. So we're sort of stuck, and there are already signs that Moore's Law is kind of saturating. I don't know about you, but I seem to buy a laptop every couple of years, and they're not getting any better. The batteries are getting better, the disk drives are getting a little faster, but the processors aren't getting any better. So I think we're already seeing signs of a saturation of Moore's Law. And again, I don't want to put too many words on slides, and this is going to be the most dense slide we have. But there's a quotation here. You don't have to read it. I'll read it for you. This is from a man named Richard Feynman, who is one of the most famous American physicists, really one of the father figures of quantum physics. And he was a tinkerer. He liked to play around with things. He was always a follower of high tech. And back in the 50s, when transistors were made solid state, he was very excited because he saw the opportunity to shrink things. And I highlighted and read this quote of his, which was 30 or 40 years ahead of its time. He said, "When we build circuits down to single atoms, there will be complete new opportunities for design." So he didn't see a problem with it. He saw an opportunity. And the opportunity is that when you get down to single atoms, the laws of physics change. And those laws of physics it's called quantum physics. And the reason they change is because atoms are simple structures. And it's really hard to get your head around this idea. And I want to tell you in very low level terms, but accurate, what we think of quantum physics, what it is, and why it's an opportunity. Okay. So when I teach quantum physics, I often do it from a information point of view, bits, zeros and ones, and so forth. And I'm going to do that here as well. But the good news is that in quantum mechanics, it's not nearly the rules are not as hard as you think. In fact, I'm going in one slide with not much density. I'm going to spell out the rules of quantum physics, and there's really nothing more to it, believe it or not. The problem is, and what makes it confusing, is that there are actually two rules in quantum physics, not just one. And the problem with that, especially in physics we love to think we're the king of science. We have one law at the very top, everything, even though it's maybe useless to do this, you can apply every known phenomena in nature to this one law. Well, in quantum physics, there are two pyramids, and you can't relate one to the other. You can see why that would drive mathematicians and theoretical physicists crazy. We think we would love there to be one law on top of those two, but so far unsuccessful. So that's sort of the weird thing. It's more, you could argue it's a sociological problem. We like to see one law at the very top. Even F equals ma, Newtonian physics, all mechanics comes from that. We don't have that in quantum physics, and that's part of the problem with it. But you have to get over it. Einstein, unfortunately, never got over it, and he always thought there was going to be a law at the very top, and he died not knowing what that law could be. But it turns out that if there is a law at the top, it's at least as weird, and I'll tell you what I mean by that. So, two rules of quantum mechanics. I call them the golden rules, and there's only two. And each of them by itself is pretty easy. Okay, rule number one. Ready? Here we go. Quantum systems are actually waves. You've probably heard this. This cup of beer is actually a wave. Okay, fine. Particles are waves, whatever that means. Okay, well, waves are fine. We're quite familiar with waves in all kinds of different contexts. Waves on a rope or water waves on a pond. Well, one property of waves that we're very familiar with is the idea of superposition. Sound waves, for instance, you can experience many different tones at the same time. Your eardrum will vibrate in superposition, and your brain can decode this complex sound you hear as whatever notes they are. When you throw a rock in a pond, where is the wave? Well, it's everywhere, and it's expanding. So the wave, the crest of that wave is distributed. So the concept of superposition is not a big deal when you think about waves. Now, reverting to information, the simplest superposition has only two parts. A general wave is very complicated, but if you imagine a system that can only be in two different states, like this beer is here and here at the same time, just a two-state system. And I use that example because number one, it's the simplest, it's the smallest case we can think of, and number two, we can use it to store information as we do bits in regular computers. So here's a picture, a poor picture of a single atom, and that blue dot is a single electron, and it's occupying two different orbits at the same time. Now, if you remember from high school chemistry, these are orbitals, and that's fine. But that single electron is indeed in a superposition of two places, and it's a wave, so it's sort of fuzzed out in two different places. Now, I put that little equation there because quantum mechanics has its own jargon. And I usually avoid jargon, but we have our own notation, and I thought you should just see that notation. This vertical line and the angle, that means it's a quantum thing. And this is expressing that our quantum thing is in a superposition of 0 and 1. The 0 could be anything. I could store a superposition of 0 and 1 with this beer. There's 0, there's 1. And so a superposition of 0 and 1 would have this beer in both places at the same time. And the parameters A and B are sort of the weightings of that superposition. It could be a 90-10, 50-50, whatever. So A and B carry information. How much 0 and 1? Now remember, this is totally unlike regular bits that can only be 0 or 1. They can't be both. A quantum bit can be both 0 and 1 at the same time with any weighting you want. And we're going to want to control those weights and so forth. Okay, simple enough, right? So this is basically what we do in the first 1 or 2 courses of quantum physics, is we describe quantum systems, but it is a wave, and so it comes with a wave equation, which is a second-order partial differential equation with complex numbers and so forth. But that's just math. There's the math. It's called the Schrodinger wave equation, but I don't need to talk about it at all. All I need to tell you is that A and B change in time. We can control it. This is the dynamics of the wave. And it's complicated. Every waveform is complicated. Water waves are incredibly complicated to describe them mathematically. In fact, here's a very pretty picture. And I copied the wave equation for surface waves in shallow water. I don't know how to solve that. I don't even know what those variables mean. I mean, well, I think they mean sort of the height of the wave as a function of x and y position. But we all know that wave is going to come crashing down. And when you're at a beach, we all know that waves, they gather height as the water gets shallower, and they get like this, and then they finally crash over. The mathematics is incredibly complicated. No more complicated than quantum mathematics, by the way. So, how much understanding do you get from solving these equations? I think if you're an expert in fluid mechanics, you have to dive in there. But for somebody like me, I don't need to solve these equations to see the beauty of a wave and even predict some things of what's going to happen to that wave. Okay? So that's the spirit with which you should think about quantum mechanics. There's a wave equation. It can get as complicated as you want. And unfortunately, usually for the first full 2 terms of quantum physics classes, we just solve the wave equation. It's like put your head down and calculate. Well, we're not doing that here. And if you are comfortable with the idea of a qubit, a bit that can be both 0 and 1, that goes a long way. Except we're missing something. And I know what you're saying, well, we're missing the second rule. Well, we're missing something because we never ever see superpositions in life. You've never seen, I'll bet you've never seen a beer bottle in 2 places at the same time. Well, quantum physics says that's possible. And the way we were sort of forced into this position because this is the behavior of individual atoms. In fact, the reason why we have atoms, the reason why the electrons, as you know, are negatively charged, the reason they don't get sucked in to this nucleus is that they're actually waves, and there's no way that wave can experience the nucleus. It's sort of like when you pluck a guitar string, there's only certain modes that you can excite. Some modes are just not allowed. And so we're forced to use wave mechanics to describe anything that's quantum. Okay. The problem is when you apply it to big systems, things are very strange because there's no connection to reality. And so that's why we have to almost invent a second rule. And this rule, unfortunately, it's a total ad hoc rule. And I'll just write it down. This is a little bit tongue-in-cheek, but rule number 2 says that wave stuff only works when you're not looking. So that sounds profound. It's a little bit of a joke, but it actually encompasses the other half of quantum mechanics that says, no, we don't see superpositions in the real world. So we're gonna pretend that quantum mechanics only applies when we're not looking. Yeah, it's quite lacking, I think. But what happens when you do look? I mean, you have to be able to look at something. I mean, if you're going to build a computer out of these things, you have to be able to measure it, otherwise it's useless. So yes, we're going to look. And this rule number 2, the extension of rule number 2 is that when you do look at this quantum superposition, it pops into a definite state. Well, that's good, because that's all we see. So at least it's consistent with reality. But there are a few things that's very strange about this. One is that it seems that the act of observing a quantum superposition changes the quantum superposition. And that's the way I think of it. It may not, philosophers run amok at this idea because the act of, there's no other example in all of nature of something that changes just because we observed it. I mean, we can be really far away and observe it, and it still changes. So you can clearly see that a whole generation of scientists rebelled at this, including Schrödinger, including Einstein, some pretty famous people. And so you can see that we would love to have a rule number 0 that somehow these things can be adapted to. Unfortunately, that's not the case. We haven't found a rule 0, and in fact, I don't think we even need to. The second very strange thing about rule number 2 is that, what happened to A and B? Remember the weightings of the superposition? Well, A and B are reflected in the probabilities of observing these two. So that's supposed to be A squared and B squared. Sorry, a little typo there. Don't worry about that. But A and B give you the probabilities of observing the two pieces, and that sort of makes sense. If the weighting of 0 and 1 is A and B, then it would make sense the probability of seeing 0 or 1 is given by A or B. And what's weird about this, if you think about it, is that, well, probabilities are always weird. Have you ever thought deeply about probabilities? They're sort of fake. Even flipping a coin. We use probabilities, it's very useful, or predicting the weather or the stock market. It's useful, but it's not fundamental. We know that when I flip a coin, I could calculate exactly what's going to happen. I don't need probabilities. But it expresses ignorance. It expresses a system where we don't want to know everything. In the case of weather, it's probably too complex to ever know it. So we use probabilities, and we're comfortable with it. We're comfortable with our ignorance, put it that way. Okay? Not so in quantum physics. It's not about ignorance. You cannot know ahead of time what you're going to get when you measure a superposition. You cannot know. That's weird. It seems to be there's a god, or there's a third party, there's some joker cooking the books in the background in another dimension or something, right? If you think about it, how can probabilities be fundamental to any theory? In fact, there's no other theory in nature where probabilities are fundamental. Okay? So rule number 2, very strange, but it works. It's been tested more accurately than any other theory in all of nature. It's been tested to 13, 14 digits of accuracy, usually in atoms and small structures. Okay, so there's very little text in the slides to follow, but one other thing I want to comment on rule number 2, and this gets kind of fun. Who says you need a conscious observer to make a measurement? In fact, you really don't. And this is where things get weird. I said weird too many times, but I'm defining reality in a way. I mean, is this system real before we observe it? What does it mean? Does it exist? So these are very interesting, more, even philosophical questions. And there are a lot of philosophers. We have one on campus who's an expert in quantum interpretations, what reality means in the context of quantum mechanics. But let's go back to the beer. I got to get working on this beer, but the beer analogy, if we imagine having this beer in 2 places at the same time and nobody's in the room, is it okay? Well, our intuition is that no, the beer cannot be in 2 places at the same time, even if there's nobody here. And that's actually sort of true. And the reason is, well, one reason is there's air in the room, right? If the beer is over here, we know there's no air where that beer is, but there is air over here. If the beer is on this side, there's no air here, but there's air here. How does the air decide where to go? Does air have a consciousness? Let's go down, let's suck all the air out of the room except for one molecule of air, and one nitrogen molecule. And let's say that nitrogen molecule is coming right where my finger is here. Well, it's going to hit that beer if it's over here, but not over here. So now this single molecule has to make a decision. Am I going to go that way? Or am I going to bounce off this beer bottle and beer cup and hit that wall? So the way we don't ascribe a consciousness to that air molecule. The way we deal with it is we invite the air molecule to become part of the superposition. I mean, hell, we have already 10 to the 23 molecules in superposition. Add one more, what's the big deal? So the way we deal with this in physics is that we invite the air molecule to be in a superposition of going that way and that way. And it's correlated with where the beer is. So we have a superposition of beer here, molecule rebounding, with beer here and molecule going straight through. That's called an entangled superposition. There's a correlation between the air molecule and this beer. And I'll talk about entanglement a little later. It's a very cool phenomenon that has no analogy in classical non-quantum physics. Okay? All right, so I spent a lot of time on rules number 1 and 2. That's it. That's quantum physics. If you don't like it, too bad, because it's right. I say it's right. It's been tested so severely that this interpretation works just fine. And I use that word carefully, interpretation. There are many interpretations of what's going on here. And in fact, I have one, sorry guys in the back, I'm going to jump ahead a couple of slides. Yeah, I'm not gonna. I think it's too complicated. So we'll stay where you are. Hold that thought on interpretations. Well, I mentioned sound waves and superpositions. You might ask, well, we don't see superpositions in nature. I don't really understand them. How can I understand what these things are? Is there an analogy? Well, there are a few analogies. They're a little strange. They usually involve illusions, like auditory illusions or optical illusions. And there's one of my favorite optical illusions, and you're probably familiar with this one. So next slide. This is when you try to draw a cube on a blackboard. You only have 2D to convey a 3D object. And this one, all the lines are parallel, so they don't have the perspectives wrong. I mean, it's an ambiguous perspective in this drawing here. So the question is, which face is the front face of that cube? Well, you can see it either way. And in fact, if you kind of look at it, you can see it sort of flop back and forth maybe. It's a little bit like a 50-50 superposition. Okay? And the neat thing is, when your mind locks onto a particular perspective, it's sort of like rule number 2. you make a measurement. So that's kind of a cool analogy for a single qubit. Well, and here are the two definite perspectives, of course. Front face down and to the left, up to the right. So this concept of entanglement can be taken very far. I mean, I think the beer analogy is, I mean, this is a huge system. We're not used to describing it according to quantum mechanical terms. I mentioned Schrödinger, who was one of the founders of quantum physics. He has a very famous treatise. It's a very long paper where he's sort of rebelling against the idea of quantum mechanics, and he invents this. He invents this this experiment, this thought experiment called Schrödinger's cat. It's actually a very simple device in a way. The idea is, if you bear with me, the idea is there's a single atom in a box, and it's a radioactive atom. And we know a radioactive atom can be, if you wait one half-life and it's not observed, it's in a superposition of its original state and its decayed state. And so after one half-life, the atom is actually in a probability distribution of those two. And if it's hooked up to a Geiger counter, a perfect Geiger counter that registers a click or not, that Geiger counter can be tied to a hammer that smashes a flask of poisonous gas. And if that gas is released, it kills the cat. So the idea here is that that simple superposition inside of an atom immediately got transferred to the livelihood of this cat. So the cat has to be considered both dead and alive. It's a little bit like the air molecule on the beer. This is a little more diabolical, I guess, but you've probably heard of Schrödinger's cat. This is in 1935, and Einstein had his own paper calling into question quantum mechanics. I mean, could this be the real theory if it predicts weird things like this? And quantum mechanically, we would write the equation if we wanted to describe the situation. It's an entangled superposition of the atom in 0, and a live cat, with the atom in 1 and a dead cat. And you know, to me, the most interesting and the most difficult part of this experiment, you know what it is? It's not the cat. It's not the single atom, believe it or not, in the Geiger counter and the flask. It's the box. It's the box surrounding the cat, because we can't have air. What if we're in that box with the cat? I mean, so isolating something turns out to be very hard. And rule number 2, remember the one that says that superpositions pop out randomly. To prevent rule number 2 from spoiling everything, you have to have extreme isolation. If I really want this beer in 2 places, there can be no air, there can be no light hitting it. It just has to be perfectly isolated. And that makes it very hard and quite exotic to observe some of these things. So continuing to my analogy, this cube I showed, it actually extends to entanglement. Because when you draw 2 cubes right next to each other, this is the only analogy I know of entanglement. You can see that if you think of each cube as a bit, 0 or 1, you'll probably find that the perspectives of these 2 cubes are the same. You probably can't predict which one you'll see, but you'll see them to be the same. So this is sort of like an entangled superposition. And when your mind locks onto one, it stays there. Rule number 2, right? You only see a definite state. Now your mind, this is an imperfect analogy, especially when you separate the cubes. Your mind can make one have one perspective, one the other. So it's imperfect. I mean, after all, this is not a quantum system. Okay, so I mentioned I know this is very pedagogical, but it's important I think we need to understand technology that could come from this, and I'll get to that in a minute. We need to have a culture where these 2 rules aren't so weird, or at least, I mean, they can be weird, that's fine, but we need to be comfortable with them. And we're not quite there. In physics departments, in chemistry departments, and math departments, we're fine. But if you go to IBM or Google or Boeing, the engineers there, they almost don't believe it. It's and that's a real problem. If we want to build something, we need professional engineers to drink the Kool-Aid, to drink the beer. I guess it doesn't help that we have all these different interpretations. I mean, so I've shown you my interpretation, which is the common one. It's sort of one of ignorance. All right, we have these 2 rules. Just don't ask questions. When you look at a quantum system, it randomly pops into one or the other. Just deal with it. In fact, there's no experiment that can tell the difference between that interpretation and other interpretations. One of my favorites is called the many universes or the many worlds interpretation. The nice thing about this interpretation is there's nothing weird, there's only one thing weird about it, but it nicely ties everything up. It basically says that when you have a superposition and you make a measurement, right at that moment the universe splits into two if you have a bit. And you saw your version with some weighting, and your other universe version of you saw the other state. Okay? So every time a measurement's made, the universe splits. So there's a gazillion universes. And so it neatly ties everything up, I guess. That's one rule at the very top. There are many universes. I guess it works. To me, it's very unsettling. Partly because we don't know how to travel between these universes if they exist, so we can't test it. And in fact, any observation with this interpretation will be the same observation in the interpretation I gave you of the two rules. So I guess I tend to, and most of the community sticks with that interpretation where we just don't have a single rule at the very top. If that's okay with you, then you can use it. All right. Okay, so let's move on to technology. I guess my title was What Quantum Computing Can Do for You. Well, what is a quantum computer? Well, a quantum computer takes many quantum bits and puts them together. And things get very complicated very fast. This is partly why we have no way to model complex systems fully quantum mechanically because they're too complicated. And here's one, it's not hard to see why that's the case. One bit can be in two states at the same time. 2 bits can be in 4 states at the same time. 3 bits can be in 8 states. So you can see we have exponential. By the time you get to 10 bits, that's 1,000 states. 20 bits is 1,000,000 states. What about 300 bits? If you have 300 bits, in principle, there are 2 to the 300 configurations, because there are 2 to the 300 bit numbers. And the reason I picked 300 is that 2 to the 300 is about 10 to the 90, give or take. 10 to the 90. So that's more than the number of particles in the universe. With just 300 bits, 300 atoms, 300 photons, 300 electrons, in a sense, that simple system can deal with a number of configurations in superposition that you could never store. Even if every atom in the universe is part of a regular computer, you couldn't store it. There's not enough space. So this is a quantum computer takes advantage of that exponential growth, and in a sense, it allows us to continue, maybe for certain applications, to continue on our own version of Moore's law. And this, I think, is the opportunity that Feynman saw back in 1959, and it's finally starting to play out after about 30, 40 years. So this field, it's been a little bit nascent, a little bit quiet for the last 20, 25 years or so, but in the last 5 years, it's you can't read a science story without hearing about quantum computing, quantum this. Frankly, there's a lot of noise in the field, and we don't know what to make of it because nobody's really built a useful device yet. And worse still, we don't know exactly what they're useful for. I can give you some hints. Well, probably the most well-known application is unfortunately among the hardest. It requires many, many quantum bits, maybe 1 billion quantum bits. And I'll fast forward and tell you that the state of the art is right now about 20 to 50 quantum bits, right? And those are heroic experiments. How about 1 billion? Control 1 billion particles at the quantum level and make a superposition of those. Well, this problem I'm talking about, it might sound rather narrow and esoteric. It's factoring of numbers. Factoring in numbers into their prime factors. Like 15 is 5 times 3, which is easy because it's a small number. But if I give you a number with 1,000 digits, you cannot factor it into a couple of 500-digit numbers, which when multiplied together give you the original. That sounds like an esoteric problem, but it's actually the core. It's the core behind almost all of the crypto systems we use now to encrypt data, including your credit card on the internet. There's a big number made public and nobody can factor it, and that's why your credit card is secure. So you better believe the folks up in Fort Meade are very interested in quantum computing because if a quantum computer exists, it calls into question all of our encryption standards. The good news is that we're not even close to having a quantum computer at that level, but the NSA needs to know when. Is it 20 years from now? Is it 10 years? Is it 30? Because you might want to keep secrets for a long time, political timescales. So, in fact, it's very important for the U.S., for governments to know what it takes to build a quantum computer and when we might have one. But that is not the application we're going to see, maybe not even in my lifetime, and I'm 50. So there are hints of other applications that are they're much easier in a way. They don't involve so many qubits. And they actually are more science-y in a way. One of them, I mentioned molecular structure. Individual electrons can have lots of configurations, and you can use quantum computers to actually simulate the behavior of molecules or simple quantum systems where your PC or your supercomputers don't work so much anymore. And strangely enough, that problem of solving the electronics of some complex molecule doesn't sound like it, but it turns out that's a very similar problem to the traveling salesman problem. You know what the traveling salesman problem is? This is a classic, very hard mathematical problem. If I give you a map with a bunch of cities, say 200 cities, your task is to find the shortest path between all of them, visiting all of them exactly once. Well, that's a real hard problem. There's too many configurations. Well, a quantum computer, very much like the molecule, a quantum computer might be able to solve an approximate the solution much better than we could any other way. So I'm sorry to say I can't point to something a quantum computer will do in the next 5 years. I think we need to build machines and get them out there, have people play with them. And that's what happened with regular computers, by the way. In 1950, the solid-state transistor, nobody knew what it was going to be used for. Nobody could imagine you could pack 10 billion of them in a chip. They were talking about, you know what the market was for the first transistor? A portable amplifier for hearing aids. I mean, talk about a small market where you could put 10 transistors in your pocket without vacuum tubes, okay? So predictions of the future are always wrong. So that gives us more confidence that we should try to build these things and see what happens. Okay, so now I'm going to tell you a little bit about the research we do on campus as a leading group playing with these individual atoms. And this is a, let's see, it's supposed to be an animation. Yeah, there you go. This is a animation of individual atoms that are being loaded in something we call an ion trap. These atoms are charged. Each one of them has a positive charge and they repel each other. They form a crystal. And for scale here, left to right on the screen is about 0.5 millimeter or something, maybe 1/3 of a millimeter. So it's pretty small, but not super small. Now you might be asking, how come I can see single atoms? It's a good question. You don't usually see single atoms. Well, this is an exotic system. There's no air. These atoms are floating above electrodes. There's nothing else there. So when we shine laser light on these atoms, and that laser is tuned to a very particular color, when I say very particular, I mean we tune it accurately to about 10 digits, and it's stable. And so there's a lot of electronics that goes behind that, but that's actually the easy part. So you see these atoms because they're glowing when we shine light on them. It's a beautiful quantum system. It's the most pure quantum system we know of because each atom is the same. In fact, you can see a gap. If you look closely, that atom is not the same. I think it's a different isotope. These are atoms of ytterbium, Yb, and they're all the same except for that one. And so they're sort of, you can replicate them, you can think of scaling up. And we use laser beams to poke at these things. We store information in these things, and we make quantum computations. Now, in fact, I have my lab on a Skype line, and I'm going to, let me duplicate this. I'm going to call them in the lab. And sometimes this works. Let's see. Hello there.
Hi, Chris.
This is Wenlin Tan, a graduate student. Who else is there?
Guido, Javi.
Guido Pagano is a postdoc, and Harvey Kaplan is also a graduate student. And soon you'll see a picture from the lab. They're only about a quarter mile away in the dark, deep, dark basement of one of our physics buildings, and they will share their screen showing a live picture of individual atoms and lots of stuff. They're editing a paper there. There it is. Okay. It doesn't look as fancy as the one I showed you before, but this one's live. Those white dots, can you see them? Those are all individual atoms in a string, and right now they're poking a laser at them and they're doing experiments. They're building quantum gates. It's sort of like individual transistors. And the cool thing about these atoms is that they can be in a inside the atom is sort of a magnetism, and they can be in a superposition as long as you don't look. And for us, not looking means we turn that laser light off, and it's pure darkness. The atoms are still there, but they can persist in these superpositions. A very clean system. So sorry, we're a little short on time, you guys, but just to prove that you're not playing tricks on everybody here, could you like maybe block a laser beam or do something? Make the atoms move around. They have a bunch of tricks up their sleeve. We'll see what they do here. Maybe they're going to squeeze them.
Oh, squeeze them.
Very good. So he's going to squeeze them from left to right. They'll get much closer together. I guess I still could have set this up, right? But there we go. So you can see when he squeezes them, they sort of form a zigzag in the middle there. Okay. Anyway. So this is actually, believe it or not, this is the leading candidate right now to build a quantum computer. It's exotic stuff. It involves vacuum chambers. It involves lasers. Hey, you guys, I'm as always way late on time, so I'm going to have to hang up.
Okay.
All right. Thanks.
Bye.
Bye-bye.
Bye.
Okay. Sorry. I want to save time for questions here, so I'm just going to wrap up here. Hold on a minute. Okay. I guess the bad news is that this is actually a picture of that lab. If you look at it, it's really complicated. There's lots of stuff. There's lots of equipment, lasers. I told you we tune these lasers to 10 digits, and that takes a lot of electronics and so forth. And so nobody wants to buy a computer that looks like this. And that's certainly true. But this is a research laboratory. You know, every mirror and lens on that table that has a laser in it, it has all kinds of adjustments. But if you know what you want, you don't need to be, it doesn't need to blow up like this. And in fact, there's another laboratory on campus where everything you saw on that table is in this box. And it's about 1 meter cubed. And this is a very highly engineered system, even though it's at a university. And we're funded by our friends IARPA. This is people in the intelligence community, and a bunch of companies have helped us along this way. And if this looks like a company, I mentioned IonQ is a startup just down Campus Drive, right before the train tunnel as you go down there. And we have about, this is an outdated picture, we have about 33 employees now. And we have several prototypes that we're building and testing right now over there. And it's funded by private money, and again, I lose sleep thinking, you know, what's the future of this company? We have no idea what the market is, what this stuff's going to be good for, but we're going to build something that you can use from the cloud remotely. You don't have to know anything about lasers or atoms, atomic ions, traps. All you need to know is the language of the 2 rules of quantum physics. What a gate is when you manipulate a single atom, you change the superpositions, you make entanglements in a certain way. We need to develop languages, by the way, to do that. It's a very low-level system. And then you measure them at the end of the day using lasers. You don't need to know about lasers to do that. You just need to know about quantum information. And this is what I meant. We need a culture of computer scientists that want to play with our system. And maybe they can come up with something interesting. That's historically what's happened. When you make devices, they go in directions that you cannot predict. And there are lots of smart people out there, way smarter than us, on algorithms, complexity, applications from finance to autonomous navigation, pattern recognition, that quantum systems might be able to do that you couldn't do otherwise. So that's my last slide, and I'm sorry I ran over time a little bit, but thanks for your attention, and I'm happy to take any questions.